We're happy to have Lingxiao speaking to us today. This is Lingxiao's third year here, and he'll be talking to us about privacy and federated learning.
Information from the training. For example, I used to play with GPT-3 to use some prompt to recover the exact content in some copyright books. And some studies have shown that for the generative models, you can generate the specific image of yours. Therefore, to alleviate these privacy leakage issues, lots of privacy-preserving technologies will be developed. One widely used technique is to achieve differential privacy in the training of the machine learning model. So the situation here is that if the algorithm is differentially private, changing one individual data record will not change the output distribution by much. For example, if I change Alice data with Annie's data in your training dataset, you cannot infer whether Alice or Annie is in the training dataset according to the output of your machine learning model. More formally, we see a randomized algorithm is epsilon delta differentially private if for all the neighboring datasets we have the following input. And another emerging technique in recent years that prioritizes the privacy is federated learning. So Carroll et al. Defined federated learning as a collaborative setting where multiple clients or devices and a central server try to solve a machine learning problem without exchanging or transferring a client's raw data. So from the privacy-preserving perspective, federated learning can also be considered as a data minimization technology, since federated learning structurally embodied the principle of data minimization. For example, federated learning can minimize the data exposure by storing the data locally, and we only need to send focus updates such as gradients or model parameters instead of raw sensitive data to the server. And we can also discard client's information after each aggregation. However, federated learning itself can still leak sensitive information of your training dataset, since it does not provide formal privacy guarantees, such as differential privacy of the released output. So in this talk, I will mainly focus on these two techniques. As the first part of this talk, I will discuss a specific overparameterized problem with differential privacy guarantees. And the second part of this talk, I will look at the optimization as well as how to achieve differential privacy in federated learning. So first, let's look at the private overparameterized linear regression problem. And the motivation of studying this problem is actually due to the failure of differentially private machine learning algorithms for large models. And we want to understand in which scenario differentially private machine learning methods can handle the large models. So as a starting point, we consider the overparameterized linear regression. So the goal here is that given a dataset consists of capital N data pairs, we want to find a model parameter that can ensure differential privacy while achieving a small access risk. And LW here is defined as follows: the expectation of the square loss. And X is a feature vector, and Y is the response. W star is a minimizer of LW. And we also assume the model noise to be zero mean with some various parameters. And we are particularly interested in the overparameterized regime, such that the feature of model dimension D is much larger than the number of training data. It can be even infinite. And this setting has been considered in many previous work for non-private linear regression. So here are several works have studied the private linear regression problems. For example, one can use differentially private gradient descent or DPSGD with random shuffling to solve the private linear regression problem to get the following access risk. However, this bound will explode when D is larger than N. There are several other works consider the more general problem, such that the per example objective loss is convex and Lipschitz. It shows that for DPGD or DPSGD with growing batch sizes can achieve the following access risk. And you can see here that these results do not explicitly depend on the problem dimension D. And the parameter R here can be much smaller than the dimension d, or even the number of training samples. However, this result cannot be applied to private linear regression due to the Lipschitz assumption. There are also some other terms for solving high-dimensional private linear regression that achieves dimension-independent empirical risk. However, these methods often assume sparse model parameters and restricted, strongly convex or smooth objective ones. So one natural question we want to ask here is that, can we achieve a tight or even dimension-independent exit risk for private linear regression in the overparameterized regime? So to answer this question, one major motivation here is that there are several works have shown that SGD for non-private overparameterized linear regression can achieve a sharp excess risk that depends on the eigenspectrum of the data covariance matrix. Therefore, we want to develop a private variant of SGD-like algorithm for linear regression that can yield similar excess risk. Therefore, we propose a new differentially private for the rigorous leader method, which we call it DPFTRL sigma. It is based on the following DPFTRL algorithms. At this iteration, we are solving a FTRL-based optimization problem, except that we are using a private version of the prefix sum over the gradients. And the private prefix sum is obtained using the tree aggregation method. So more specifically, suppose we have a stream of data from G1 to G4, and we can store them in the leaf nodes of this complete binary tree. And the parent node in this tree stores the value of their children nodes. So given this tree, if we want to get the prefix sum, say G1 plus G2 plus G3 plus G4, we can obtain the value through the root node and add in one Gaussian noise to make it private. So here, the sigma term corresponds to the noise magnitude determined by some parameter psi, which is the upper bound of the gradient norm of all the data points. And the identity matrix corresponds to the noise shape, suggesting the isotropic noise here. Note that even for this original DPFTRL algorithm, it is unclear what is the excess risk for solving the private over-parameterized linear regression problem. This is because the regret-based analysis of DPFTRL cannot give us a tight bound. And one of our contributions is to develop such analytical tools to handle the overparameter case. So note that the additive noise here plays the role of privacy and utility trade-offs. Intuitively, stronger noise will lead to a better privacy guarantees, but can hurt the convergence of your algorithm. And the standard choice is the identity matrix. However, there are some disadvantages of using isotropic noise. For example, it may be too conservative, as some coordinates of your gradient may not have sufficient signals that need to be protected, and it may also introduce large variance error in a high-dimensional regime. Therefore, in order to address these disadvantages, we propose to make two critical modifications of the DPFTRL algorithm, especially for the tree aggregation procedure. So more specifically, we propose to adaptively estimate the norm of the gradient at each iteration, instead of using a pre-selected uniform node bound of the gradient. This allows us to better estimate the gradient norm at each iteration and leads us to a reduced amount of random noise to achieve differential privacy. And similar ideas has been explored in some previous works. And we also propose to add the random noise with a general covariance matrix with the goal of achieving potential better privacy and utility trade-offs. And I will later talk about how to design a good covariance matrix to achieve better trade-offs. And of course, as I mentioned before, we also developed new analytical tools based on the non-private method to further handle the general noise covariance matrix and correlated additive noise. So here is another overview of our proposed method. So note that we estimate the gradient norm at each iteration based on some estimating data. So if the estimating data is not publicly available, we can just split the training dataset and use some of the training data as the estimating data. And then we can use a differentially private method to estimate the gradient norm. And for the model update, we propose to use non-isotropic random noise to achieve DP in the tree aggregation procedure. So before going to the design of the noise correlation matrix and the theoretical guarantees, let's first look at the data distribution we made in our work. So basically, we assume the data to be sub-Gaussian with correlation matrix H. And the sub-Gaussianality of the data has been considered in many previous work for both non-private and private linear regression. Additionally, we also assume the following stronger assumptions for the design of the specific noise correlation matrix to achieve improved privacy and utility guarantees. So this further assumes that the coordinates are independent. So this additional assumptions is beneficial for us to sharply characterize the eigenspectrum of the gram matrix, which has also been considered in several prior works. Now let's see how we can design a good noise correlation matrix to achieve better privacy and the utility trade-offs than the identity design. First of all, here are some critical observations for the identity design. So it will introduce large variance error when the problem dimension is large. And adding the same Gaussian noise for all the coordinates may be too conservative, and some coordinates may not have sufficient signals that need to be protected. Also, the noise magnitude will also be determined by the choice of the design correlation matrix. If we have the identity design, this magnitude is actually small. So motivated by these observations, we propose the following design: sigma equals to lambda I plus h. And the goal of this design is to use stronger noise perturbation along the large eigenvalue directions of h, and the weaker noise perturbation along the small eigenvalue directions. And this is motivated by the fact that the stochastic gradient for the data pair is parallel to the feature vector. Therefore, the design of sigma should concern the data covariance matrix H. Regarding the parameter lambda here, when lambda goes to infinity, we have sigma goes to lambda times I, which is nearly the same as the identity design if we ignore the scaling parameters here. And recall that the noise magnitude sigma square will also determined by the design of your correlation matrix. When we choose sigma goes to h, as lambda goes to 0, this noise magnitude will goes to d, which explodes as d goes to infinity. So as you can see, the parameter lambda here should be a positive constant, serve as a parameter to control the noise along different directions. However, the data covariance matrix H cannot be realized in practice. Therefore, we consider the scenario we have access to a set of unlabeled public data sampled from the same distribution as the training dataset. So we propose to first use unlabeled features to generate an estimation of H, and then design the noise covariance matrix as follows. So tilde x here is a feature matrix. Note that using public data in the differentially private method has been widely adopted in the literature, and getting the unlabeled public data is generally cheaper than labeled training data. So now let's move on to the theoretical guarantees of our method. So under certain choice of the parameters of the algorithm, we show that our proposed method is epsilon delta dp. So the choice of tilde epsilon and tilde delta is to ensure that the procedure of adaptively estimating the gradient norm is dp when the estimated dataset are not publicly available. And our privacy guarantees does not rely on large batch gradients, or privacy amplification techniques, which was widely used in the previous work. These techniques will often impose stringent conditions on the privacy parameters. For example, for the DPHD with random shuffling method, it has the following requirement on the privacy parameters due to the shuffling techniques. So this constraint actually is worse, it's very bad because their method can only work for small privacy budgets, which could be too conservative in practice. And in addition, this could also lead to a worse sample complexity. And you can see here that this will give you a much worse sample complexity due to the second term in the access risk bound. And for the utility guarantees, we have the following access risk. It consists of two terms. We call it bias error and variance error. The error looks a little bit complicated here because we consider a general covariance matrix, and we will simplify it by plugging identity design and our proposed design. And several things can be noted here. First of all, this error term is introduced by the privacy mechanism, and the parameter tau here is at the order of 1 over epsilon. So if epsilon goes to infinity, which means there is no privacy at all in our algorithms, this term will disappear, and it can recover the non-private results for this problem. And secondly, you can see from the results that the error is a function of the eigenspectrum of the data covariance matrix, which is tight or can even be dimensional independent. So let's plug in specific noise covariance matrix in our results. For the identity design, we have the following access risk. So the error consists of non-private error component and private error component. And the term k star plus n times eta times the summation of lambda I can be understood as the effective dimension. So if we want to achieve a vanishing access risk, we need the effective dimension is much smaller than n. And for our proposed design, we have the following access risk. We can see that the non-private error component stays the same. And for the private error component, it is roughly as the order of eta squared times effective dimension plus effective dimension cubic over n. And if we compare with the identity design with the private error at the order of eta times effective dimension, our proposed design can achieve faster rate when n times eta is much larger than 1. And this is often the case since we want to choose a relatively large step size. And let's look at some example data distributions. Here we consider the eigenvalue of the covariance matrix H to be polynomial and exponential decay. And we have the following access risk for different designs. And the green terms here corresponds to the error introduced by the private mechanism. We can see that the design covariance matrix achieves faster convergence rate than the identity one. And if you are willing to pay for a large privacy budget, we can even achieve the utility guarantees of the non-private method. For example, for the exponential decay, if we pay epsilon at the order of square root of n, we can achieve the non-private results. Finally, we consider the privacy budget at the constant level, which is widely used in practice. We have the following access risk of our method under different data distributions. So the main takeaway here is that our results do not depend on the problem dimension, and the proposed design can achieve better access risks. So now let's move to the second part of this talk about federated learning. So in this part, we are particularly interested in the optimization and privacy in federated learning. So here is a simple illustration of federated learning framework where multiple clients or devices and the central server try to solve a machine learning problem without exchanging or transferring the client's raw data. And the server can then deploy new models to different devices. So as I mentioned before, from the privacy-preserving perspective, federated learning can be considered as a data minimization technology due to its properties of minimizing data exposure, focus updates, and immediate aggregation. However, federated learning can still cause privacy issues because the release models do not provide privacy guarantees, and the server can also observe gradients and model parameters. Of course, we can further strengthen the data minimization properties using additional technologies such as the encryption of the data or the focus updates, secure multi-party computation, or random shufflers for aggregation to achieve anonymous aggregation. And now let's first look at the optimization problem in federated learning. So we are considering the following distributed optimization problems. And with capital M machines, where each machine has its own objective FM. And we assume each machine's function as an average function to be smooth, twice differentiable, and non-convex. And our goal here is to find the approximation stationary point. And to capture how different devices related to each other, we make the following second-order heterogeneity assumptions. And it says that the hashes on the machines are close to the average objectives. Note that the quantity tau here is upper bounded by 2 times smoothness constants due to the smoothness of these functions. And we consider the access to the following stochastic n-point oracles, which can be used to study lots of class of algorithms, such as stochastic gradient descent and variance reduced methods. So more specifically, given the function g, which can be understood as a function fm on the device, it takes n input and gives you n stochastic gradient descent gradients computed using the same data point z. And we need these stochastic gradients to have the following properties: unbiasedness, boundary variance, and smoothness. And for the communication in our distributed optimization problem, we're considering the intermittent communication. So M machines work in parallel for R rounds of communications. In the figure, you can see the dense arrow denotes the time when the communication happens. And between the communication round, each machine can make k oracle queries between rounds. And for example, it can make k stochastic gradient oracles, and each machine will repeat this process for R times. So basically, there are 2 types of algorithms that can be used to solve this distributed optimization problems in the IC setting. The first one is a mini-batch algorithms. More specifically, between communication round, these machines require oracles at the same point. So one example here is a mini-batch SGD, which is often known as a fed SGD. So between communication rounds, each machine will query the stochastic gradient oracles at the same point for k times to get a large mini-batch gradient. And then they will update the model by averaging the large mini-batch gradients among machines through the communication. So it's equivalent to make R updates with batch size m times k. So we have the following convergence rate for the mini-batch SGD. And we can further improve this rate by using a 2-point stochastic oracle such as a variance reduction-based algorithm, mini-batch storm. And actually, this rate is optimal in the IC setting. This is because we have the following lower bound for mini-batch algorithms for 2-point stochastic oracles. And mini-batch storm can match this lower bound. However, as you can see here, both the upper and lower bound results do not depend on the parameter tau, which is the second-order heterogeneity parameter. So these results cannot improve with tau. Therefore, even your problem is simple with a small tau, and you would expect to benefit from the collaborations, but you cannot show that for mini-batch algorithms. And the second type of algorithm is local update algorithms. For local update algorithms, between communication round, these machines will query oracles at different points. One example here is local HGD, which is also known as Federated. So between communication rounds, each machine will query the stochastic gradient at k different points. More specifically, they are called local updates. At each step, the machine will query a new stochastic gradient at the current point and update the current model. So after capital K local updates, they will average their latest model parameters among clients through the communication. And we would expect local update algorithm is more efficient because they have more update steps. However, most of existing local update algorithms, including field average and scaffold, do not outperform mini-batch storm in theory. So the question we want to ask here is that, can we show the benefits of local update algorithms, especially to benefit from the small tau, the second-order heterogeneity parameter? So to answer this question, we first provide the following lower bound results for local update algorithms that depends on the parameter tau. So if we compare this lower bound with mini-batch lower bound, the only difference comes from the optimization term. So the local update lower bound can be much lower for small tau and large k. So the next question is, do we have such algorithm that can match this lower bound, can benefit from the tau? So the answer is yes, and we propose a communication efficient local HGD algorithm. So there are two key components of our algorithms. The first one is a variance reduction term VR constructed at the server based on the storm gradient estimator. And the second component here is a local gradient estimator based on the Sarah gradient estimator. And the blue terms corresponds to the part computed by the client. And the parameter rho here is a decaying rate to control the historical informations. And the gradient difference in the local gradient estimator will allow us to explore the effect of the second-order heterogeneity. So intuitively, the estimation error of the local gradient estimator can be decomposed into the following two terms. And the first one corresponds to the error of the server variance reduction term, which will go to 0 as the communication round increase. And the second term will depend on the parameter tau. It will also go to 0 as R increases and decrease with the tau. So as you can see here, for a small tau, we can use a large K to have more local updates. And this is how we can benefit from the low heterogeneity assumption. Here is another overview of our algorithms. As a server, we'll construct the variance reduction term using the gradient computed by clients. And the client will perform local updates using the local gradient estimator. So we have the following convergence rate for our proposed algorithm. You can see from the results here, it will depend on the parameter tau. Recall that we have the local update algorithm lower bounds as follows. So if the sigma parameter equal to 0, our method is optimal, because both for the local and for the lower bound and upper bound, we only have the first two terms. And when sigma is larger than 0, we have a slightly worse guarantee due to the rate term here. So it is very interesting to see whether we can close this gap in some future research. And experimentally, we compare our method against different algorithms, including both mini-batch algorithms and local update algorithms under different data heterogeneities. And our algorithm stays as the best one among these algorithms. Now let's move on to the privacy issues in federated learning. So as I mentioned before, federated learning as a data minimization technology can somehow alleviate the privacy issue. However, federated learning itself can still leak sensitive information when training it. For example, the release models do not provide any privacy guarantee. So it cannot defend against privacy attacks. And the server still have access to focused information such as gradients and model parameters. So it is possible for the honest but curious server to extract sensitive information from the gradients and model parameters. And recent studies have also shown that federated learning is vulnerable to data reconstruction attack. So our goal here is to achieve digital privacy in federated learning. Here we consider the following finite sum distributed optimization problem in the IC setting, which is slightly different from the previous one, where in there we consider the stochastic setting. And here, we consider each client has its local dataset with n data points. And we additionally consider the function f to be G-Lipschitz besides the smooth, twice differentiable, and non-convex. And we consider a much more challenging setting such that there is no trusted server, so we can cover the curious but honest server case. We consider the same heterogeneity assumptions. And our goal here is to find a model parameter that is differential private with respect to the whole dataset D and can minimize the following quantity. So what's the idea here? So the idea is to leverage our communication efficient algorithms and a random shuffler. So this will allow us to achieve a faster convergence rate and strong privacy guarantees without a trusted server. So recall that at the server side for the non-private method, we will construct the following variance reduction term, and we want to privatize it. So note that the blue terms are computed by each client using the following two terms. And for each term, we will make it local differentially private. For LDP methods, basically we can use different LDP methods for the mean estimation problem, as long as the output of your LDP method is unbiased and has bounded variance. For example, we can use this LDP method proposed by Ducci et al. For LDP mean estimation. So after we get this LDP gradient, we will send it to a random shuffler to generate a random perturbation of these gradients. And the shuffler will send these gradients to the server. The server will average them to get a differentially private variance reduction term. And locally, for each client, we just add random Gaussian noise to make it private. So given our algorithms, we can show that our proposed algorithm is epsilon delta dp with the following utility guarantees and communication complexities. So several things can be noted here. First, we obtain the best known utility guarantees in this problem. And we show the benefits of local update algorithms because as you can see here, our communication complexity will depend on the parameter tau instead of the parameter L. So tau can be much smaller than the smoothing parameter L. And for the mini-batch algorithm, it will depend on the parameter L. And compared with existing method, we can deal with the untrusted server and allow mini-batch gradients instead of the full gradient. And this somehow concludes the second part of my talk. Here is the conclusion and future works. So in this talk, we discussed the private overparameterized linear regression. We propose a differentially private FTRL sigma algorithm to achieve tight access risk, which can even be dimension independent in certain cases. And we also consider the federation learning problem. For the optimization, we consider the non-convex heterogeneous case, and we also consider how to achieve differential privacy in federated learning. So as for the future works, so can we consider private overparameterized problem beyond the linear regression? And whether we can apply the idea of non-isotropic noise to achieve DP to other problems. And for the optimization in federated learning, can we close existing gaps? And can we consider other settings, such as convex setting, to show the benefits of local update algorithms? And for the differential privacy in federated learning, can we further improve the privacy and utility trade-offs by considering some techniques such as personalization? And can we consider other privacy notions which will align well with some practical applications? And finally, I want to thank for my great collaborators in these projects. Okay, that's concluding my talk. I'm happy to take